Today, I will talk about higher order clustering with additional model selection. Hold this. Okay. This is a joint work with Shuoguang Yang, Loong-Fah Chong, and Kim-Chuan. So in graph clustering that conventionally stands for, it is assumed that the relationship between data points can be captured by a pairwise measure of affinity. However, in many graph systems, it does not make sense to talk about pairwise affinities. For example, 2 points trivially define a line, so there is no useful measure of affinities between 2 points. This also happens in its dual problems. Furthermore, higher-order affinities often provide more information, resulting in better performance in many applications. So in any general clustering problems, estimating the number of clusters is an inherent problem, which is known as the model selection problem. In our previous work with pairwise affinities, given a contaminated affinity matrix A, we try to recover a matrix G, which can be easily factorized to obtain the cluster indicator matrix Z. Matrix G can be considered as a perfect affinity matrix, whose rank is exactly the number of clusters. Thus, this problem is formulated like this. The inner product is to make G close to A. The PSD constraint and the rank constraint follows from the fact that G equals to ZZ transpose. The other constraints are straightforward. Since we don't know the number of clusters R, we move the rank term to the object function. Minimizing this rank term means we prefer the clustering result with the smallest class number. Then we add a sparsity term to capture the sparse nature of an ideal affinity matrix and avoid the trivial solution. So in the higher order case, we are given a contaminated affinity tensor A, and we try to recover tensor G. Similarly, the rank of tensor G is exactly the number of clusters. Following the pairwise case, we will need the inner product between A and G, and the tensor rank to seek the simplest model, which is extremely difficult to minimize. And the PSD constraint, there is no common definitions of tensor eigenvalues and eigenvectors. So even with these definitions, PSD can only be defined on tensors of even orders. But fortunately, what we really want is to preserve this spatial structure, though it is still not an easy task. Finally, there is also the practical issue of scalability. When the tensor order is large, the number of unknowns in G becomes extremely large. And sometimes even pre-computing and storing the affinity tensor becomes an issue due to the memory constraint in a modern desktop. So here we show the key theorem to solve all these problems. That is, for any supersymmetric tensor X of order at least 3, if it satisfies the following equations, any slice of X can only be either a rank 1 matrix or a 0 matrix. For example, in this order 3 tensor, it only consists of 2 different rank 1 slices. So follow this theorem, the problem can be converted into this form, in which we will minimize the rank of a matrix G hat, whose columns are obtained from the vectorized slices of the tensor. Note this Gi from I. Following theorem 1, it is clear that the rank of G hat is equal to the tensor rank. And this special structure can be well captured by the rank 1 constraint and with PSD constraint on the slices. Here, we propose a different formulation to solve the scalabilities. So because of time, thank you for your attention. Please drop by our poster for more discussion and experiments.